Okay. Any questions? Good morning, everybody. Any questions, any problems anybody wants to look at? Okay. All right. So let's go ahead then and get restarted on this chapter 6 material, which is the quantum theory and the electronic structure of the atom. So yesterday we spoke about electromagnetic waves, the different types of electromagnetic waves that make up the spectrum. We looked at a couple of calculations involving wavelength and frequency, which are two properties of waves that we can use to describe them. And then we looked at how the energy of these waves, which we call photons, individual particles of light, how the energy of those photons is related to both frequency and to wavelength. Now we're going to connect it to the atom. So we're going to take these electromagnetic waves, EM waves. And remember, we're thinking of these EM waves as like little individual particles of light, right? And so these particles are called photons. And they have energy. They have a frequency. And they have a wavelength. In a sense, those are the three properties that we'll use to describe the photons. There's a couple of other properties they have, but we won't worry about them in this course. So the relationship that we looked at yesterday was that the speed of light is a constant, and that is equal to the wavelength times the frequency. So this is wavelength, this is frequency, and this is energy. Okay. And then we said that you could relate the energy of the photon to the frequency or to the wavelength. Okay. So those are our relationships that we can use to describe them. So now let's take a look at the simplest atom that we can make. And that's hydrogen. Hydrogen is the simplest atom that exists. It's really, really simple. In general, it has one proton and one electron. Now, there are isotopes that have a neutron, but the vast majority of hydrogen is just this two-body system of a proton and an electron. And we can think of the atom, the hydrogen atom, as having the proton in the center. So there's our proton. Remember, the proton is positively charged. And the electron, we can think of that as a negatively charged particle that's in orbit around the proton. So this will be our negatively charged electron. Okay, so proton, electron. The proton is in the center. And if something is in the center, we call it the nucleus. So this is the center of the atom. Okay. Now, the reason we're interested in hydrogen is because it's so darn simple. It's just got two particles in it. So by having two particles, you can't get any simpler than that. And then based on that, we could look at more complicated elements or atoms. So here's our proton, here's our electron. The electron's in orbit, right? It's moving around the proton. Now, what happens is, what's interesting is that if you give these atoms, these hydrogen atoms, energy, and there's different ways to do that. One way is by heating them, by adding heat. They start moving faster, they start colliding more violently. That's one way to do it. You could put electricity in, so you could put in electrical current. That gives them more energy. You can also have them absorb photons. They can absorb photons. So what you can do is you can put in a photon, and a photon has energy. And sometimes what will happen is the photon gets absorbed by the atom. by the hydrogen atom. It'll get absorbed. And what's observed is when that happens, I'll draw a little arrow down here to show what happens, is the electron will move to an orbit that's further away from the nucleus. Okay, so the photon disappears. It no longer exists. It's gone out of existence. But the energy that it carried is transferred. Let me move the the nucleus a little bit to the center. But the energy that the photon carries is transferred essentially to the electron. And so now the electron has more energy. Okay, so somehow the electron went from this smaller orbit to this larger orbit, right? That's called a transition. So a transition is where an electron moves from one orbit to a different orbit, okay? And there's a difference in energy. So I'm going to do the following. I'm going to call this state 2, meaning it's the final position or the final orbit of the electron. And I'm going to call this state 1, the initial orbit of the electron. And each of those states has an energy. So this one is E2. That's how much energy the electron has. This one here is E1. That's how much energy the electron there has. And there's a difference. They're not the same amount of energy. The further away an electron moves from the nucleus, the more energy it has, essentially. So I'm going to say there's a difference in these two energies, delta E. And that difference in energy is the energy of the electron in the second state, so that's over here, minus the energy of the electron in the initial state, in the first state, and that's this one right there. And we're going to call that difference in energy E2. Now, it is convenient to, because these are just numbers, it's convenient to actually represent them in a particular way. And the way that we represent them is with what's called an energy level diagram. So let's talk about energy level diagrams. Okay, this is a particular way in which we represent the energy of an atom. It's not used just with atoms, but it's really convenient to use with atoms. So let me draw a little picture here. Imagine, there's our nucleus, that you have these different levels, these different orbits the electron can exist in. And I'm going to number them. 1, 2, here's 3, here's 4. And you can go out further and further. I'll just so it doesn't take up that much room, I'll do this. I'll go 5 and 6. And in theory, there's no limit to how large that number can get. Okay, and we're going to call those numbers, those states, n. The symbol we'll use for them is n. So n can be 1 or 2 or 3 or 4 or 5 or 6, all as far as you want to go. But it's important to point out that as n increases, the energy increases in this direction. So in other words, if an electron is, let's say, up here, it would have more energy than it would have if it were down there, closer to the nucleus. So the closer it is to the nucleus, the less energy it has. The further from the nucleus, the more it has. Okay. So let's do the energy level diagram. Here's what I'm going to do. I'm going to plot this out. These can be calculated, but I'm just going to show you a rough diagram. So this diagram is not perfectly quantitative, but it's approximate. So here's the energy level for n equals 1. Here's the energy level for n equals 2. Here's the energy level for n equals 3. for 4. And again, I'm just going to stop at 6. You could go further than 6, but I'm going to stop at 6. Oops, that's 5. And then here's 6. Okay. So that's called an energy level diagram, this one right down here. What you're doing is you're just saying, look, each orbit has a specific energy. It has a number, 5,000 or 6,000 or 2,000. I'm going to represent those energy levels with these little horizontal lines. And now the reason this is useful is because it gives you a method for calculating delta E. So delta E would be the final level minus the initial level. And so let me give you a little bit of notation here. Suppose we say an electron in a hydrogen atom undergoes a transition. How do I spell transition? Transition from the n equals 5 level to the n equals 2 level. Show an arrow that represents this process. Okay, so what I'm going to do is I'm going to say we're going from the n equals 5 to the n equals 2 level. So what we're saying is the electron starts off here at n equals 5, and it's going to undergo a transition to the n equals 2, right? That arrow is representing the electron moving from the 5th level to a closer orbit, closer to the nucleus, the n equals 2 level. Now, show by calculation the energy change when this happens. Okay, so I'm going to put some numbers here. I'm going to put, let me move the energy because it's in the way. Okay, so I'm going to put 3,000, 2,600, 2,100, 1,500, 700, and 100. Okay, so I put some energy numbers there just so that we could do the calculation. Show by calculation the energy change when this happens. Okay, well, the energy change, delta E, is the final energy. That's where the electron ends up, minus the initial energy. That's where it starts. So it started at n equals 5. That's pretty simple. It started right over here. So if it started there, the energy is 2,600, right? And then the initial was 700. I'm sorry, I'm sorry. Let me get this straight. My mistake. It started at n equals 5, and then it ended. So this is your ending. And this is your start. So my mistake. Okay. So it's the final minus initial. So the final is where it ends up. So that's n equals 2. So that's right over here, 700. Minus the initial started over here at n equals 5, which is 2,600. Okay. So 700 minus 2,600, you get minus, was that minus 1,900? Typically, the units are in joules or kilojoules or zeptojoules, but some unit of joules, okay? And there you go. I'm not going to put the units in there because I made these numbers up, so the units wouldn't be right, okay? So the difference in energy is minus 1,900. Now notice it's negative. And so what does that mean if it's negative? What that means is the atom, the electron, if it's negative, that means it lost energy, right? Negative in terms of energy means you lose the energy, okay? So here's the question is then, if it lost energy, so in this process, the atom lost energy. Where did it go? We have this thing called the conservation of energy, conservation of mass law. You cannot create nor destroy energy in the universe. So where did it go? It had to go somewhere. And the answer is it left the atom. The energy left the atom. So how does energy leave an atom? There are different ways in which energy can leave an atom, but one important way is by creating a photon. A photon will be created in this process, and the photon will just fly away at the speed of light, exiting the atom and moving off into space. And we would perceive that, if the wavelength is correct, we would perceive that as visible light. So when the value is negative, that means the atom lost energy and a photon will be created, which leaves the atom, flies away at the speed of light, okay? This is called emission, E-M-I-S-S-I-O-N. Emission is the case where the electron moves closer to the nucleus. The energy change is equal to the energy of a photon, which leaves the atom. That's called emission. And that is a type of transmission. So when you see the word emission, the sign of delta E is going to be negative, and that means the electron is moving closer to the nucleus, and a photon is created in that process. But we can have the opposite as well. We can do the following. We can take a photon, and if the photon has exactly the right amount of energy, meaning let's say it has the same amount of energy as the difference between n equals 2 and n equals 5. So this is 5, 4, 3, 2, 1. So if that energy of that photon matches those two energy levels, the difference between those two, then the opposite process will occur. So if the photon matches this energy difference between 2 and 5, then what will happen is the photon goes in, and that's called absorption. So if delta E is positive, not negative, but positive, then a photon is absorbed, and the atom has more energy. Okay, that's called absorption. So those are the two opposite processes. Emission, a photon is released by the atom. That's when the electron goes down to a lower level. The opposite is the photon gets absorbed by the atom. The electron moves to a higher level, to a higher value of n. And the sign convention is if delta E is negative, that means it's emission. And if it's positive, that means it's absorption. Awesome. So let's take a look at a problem then. Let me see if I can pull one up here. Here we go. Okay. So each level has an energy, right? So each level has an energy, and you can calculate that energy. The energy is equal to, the energy of each level is equal to negative R divided by n squared. So n is that number 1, 2, 3, 4, 5. Okay. So R is a constant. This is called the Rydberg constant. And it's equal to 2.178 times 10 to the minus 18 joules. Okay, so that's another constant. That's, I think, our third constant we've looked at so far. We'll see there's a bunch of constants in this chapter. So you can calculate the energy of each level in this hydrogen atom. Remember, this is only for hydrogen. And it's equal to this relationship right there. Negative R divided by N squared. So that allows you to calculate delta E. So you can do E final minus E initial. So let's take a look at a problem here, okay? In a hydrogen atom, the electron undergoes a transition from N equals 4 to N equals 6. Calculate delta E for this process. And then use delta E equals energy of the photon, which is equal to hc over lambda, to find the wavelength of the photon absorbed. Okay, so notice it says the photon is absorbed. It's going from N equals 4 to N equals 6. So if N gets larger, that's going to be absorption. Okay, so let's take a look. Let's do the first part, which is let's calculate delta E. We're going to use this one right here. So here's how I'm going to do it. There's different ways you could derive a solution to this, but I'm going to show you one way. And the first way, or the way I'm going to show it, is I'm going to do E final. I'm going to calculate that first. Then I'm going to calculate E initial. And then I'm going to calculate delta E. Okay, so let's do E final. So the electron goes from N equals 4 to N equals 6. So 6 is final and 4 is initial. It's going from initial to final. Okay, so let's do E final. So E final is minus R over N squared. So minus 2.178 times 10 to the minus 18 joules over N squared. N is 4, so that would be 4 squared. So we just calculate that value. Pretty straightforward. 2.178 times 10 to the minus 18 divided by 4 squared is 16. And you get 1.36125 times 10 to the minus 19 joules. Okay, the units are joules. Now let's do initial. Minus R over N squared. So minus 2.178 times 10 to the minus 18 joules over 6 squared, which is 36. Let's try that one. So I get minus 6.05 times 10 to the minus 20 joules. Okay, now I can do delta E. So delta E is going to be E final minus E initial. So minus 1.36125 times 10 to the minus 19 joules minus 6.05 times 10 to the minus 20 joules. Now, if it helps you, you can recall that subtracting a negative number is the same as adding a positive. So you could simplify this a little bit and make it plus 6.05 times 10 to the minus 20 joules. Okay. Let's see, did I get that right? Okay. That number is smaller. Looks like it's going to get a negative. Okay, well, let's go through it. Let's figure it out. Okay, so 1.36125 times 10 to the minus 19 make that a negative, plus 6.05 times 10 to the minus 20. And I get negative 7.5625. Times 10 to the minus 20 joules. Okay, let me check that out. That seems, the sign doesn't seem right to me. Energy level for the hydrogen, so E final, so we're going from 4 to 6. Oh, yeah, so over 6. Oh, I see, I made this mistake again. It's going from 4 to 6, I'm sorry. So 6 is final. So I made that mistake twice here. Okay, let's go over this. It's easy to get it confused. It's going from 4, so that's initial, to 6, so that's final. So the 6 is final, and the 4 is initial. Okay, so this right here is initial, and this one right here is final. So I had it reversed. I had, the final is the initial, and the initial is the final. So let me do the delta E again. So it's final minus initial. So minus 6.05 times 10 to the minus 20 joules, minus a minus, which is plus 1.36125 times 10 to the minus 19 joules. Okay, so just make sure we're clear on that. It's going from, so that's initial, to, so that's final. So the 6 is final, right? 6 is final, and then 4 is initial. So then it's the one that has the 6 minus the one that has the 4. Okay, so there's our delta E. So let me try, it just changes the sign. So it becomes plus 7.5625 times 10 to the minus 20 joules. Okay, and again, the reason that I could tell that I'd made that mistake is because I remembered, wait a minute, I just said in the earlier slide, if you get to a larger number, if you're going from 4 to 6, then that should be positive. And if you're going from a larger number down to a smaller number, that should be negative. So since we're going from 4 to 6, we're going up, that should be positive, right? So when I saw that it was negative, when I did the arithmetic and I saw that it was negative, that told me that can't be right. If we're getting to a larger number, it should be positive. So that allowed me to catch that mistake. Okay, so now we've got delta E. And so that was the first question. We wanted to find delta E, but now we want to use that delta E to find the wavelength of the photon that's absorbed, right? It says absorbed because, again, we're going from 4 to 6. That means that's absorption. So let's go ahead and do that. We can use this relationship right here. The energy of the photon is equal to hc over lambda. So here's the logic behind transitions. The logic is we're using this formula here for the atom. That's the hydrogen atom. But this is related to a photon. The photon is getting absorbed by the atom. So the difference in energy of the atom is equal to the energy of the photon. But I'm going to be a little bit careful here. I'm going to have you do this. Delta E, and I'll just write that this is for the atom, is equal to the absolute value of the photon. Okay, so you remember with absolute value in arithmetic, when you say it's the absolute value, that means that you're going to always get a positive answer. So if you get negative for delta E, then just make it positive. Okay, so energy of the photon is equal to the absolute value of delta E. I actually should have written it that way. I should write that the absolute value of the energy of the atom is equal to the energy of the photon. So that's equal to that. So that's equal to 7.5625 times 10 to the minus 20 joules. Okay. Now we can use that relationship. Let me go ahead and I have that number there, right? So let me save this one. So delta E, E of the photon equals hc over lambda. We want to find the wavelength of the photon. So how do we do that? Let's do the arithmetic. If we take E equals hc over lambda, and we want to find lambda, one way would be to multiply both sides by lambda, because lambda over lambda is 1. So now we have lambda times E equals hc. The next step would be to say, let's divide it by E, both sides. And now you have lambda equals hc over E. Okay, so there's our relationship between wavelength and energy. Now we have wavelength. So H again was a constant, 6.626 times 10 to the minus 34 joules times seconds. That's a constant we looked at yesterday. The speed of light is 2.9979 times 10 to the 8th meters per second, a second constant we looked at yesterday. And then we're going to divide that by E, which is 7.5625 times 10 to the minus 20 joules. Pretty small numbers, right? So the only number that's large is the speed of light, but the H is tiny, 10 to the minus 34. And then the energies usually are 10 to the minus 18, 10 to the minus 19, 10 to the minus 20. So now we can go ahead and do this calculation. 6.626 times 10 to the minus 34 times 2.9979 times 10 to the 8th divided by 7.5625 times 10 to the minus 20. And you get lambda equals 2.6267 times 10 to the minus 6 meters. Take a look at the units. Joules divided by joules, seconds divided by seconds, and so you're going to be left with meters. Wavelength should be in meters, frequency should be in 1/seconds, energy should be in joules. Okay, so now we have the wavelength in meters. It is not unusual for textbooks or for laboratory experiments to want the units using prefixes. So let's choose the appropriate prefix. So the prefixes we have that are less than 1 is if a number is, let's write it in scientific notation, 10 to the minus 1, we typically use deci, and the abbreviation is a D. If it's 10 to the minus 2, that's centi, and the abbreviation is a C. If it's 10 to the minus 3, that's milli, and that's a lowercase m. And if it's 10 to the minus 6, that's micro, and that's a mu. If it's 10 to the minus 9, that's nano, and that's n. And then if it's 10 to the minus 12, it's pico, and that's a small p. So if we look here, we see 10 to the minus 6. So it looks like micro's the best one to use right there. Let's use micro. So this would be 2.6267, and then 10 to the minus 6 is micro, so micrometers. Now that probably has too many significant figures, because if you recall, we used 2.178 times 10 to the minus 18 joules, and that looks like it has 4 sig figs. So let's round it to 4. 2.62. So that's 1, 2, 3, 4, 7 micrometers. Okay. So that would be the wavelength of the photon that is absorbed by the hydrogen atom, right? So remember going back to the beginning, we were starting at n equals 4 and we were going up to n equals 6. So we said, look, if the number gets larger, if n gets larger, that means it's absorption. And so now we knew what the energy was. The energy of the photon was 7.5625 times 10 to the minus 20 joules. That's how much energy it has. But now we know the wavelength of the photon is 2.63 approximately micrometers, which is what we would call microwaves. So when the electron goes from the n equals 4 level to the n equals 6 level, that would be microwave. It would be a microwave radiation that gets absorbed by the atom during that process. Micrometers is typically microwaves. Okay. All right, there we go. So that's the hydrogen atom, and it gives us a physical sense of how photons are created and destroyed in our universe. So when you see something, so for example, let me draw a little picture so you can kind of understand this, if you don't already. Let's say that you have a light bulb. And that light bulb is sending light across the room. You turn the light bulb on, or someone else turns the light bulb on. Your eyeball, essentially what happens is, there's your eyeball. Essentially what happens is these are individual photons, right? Countless numbers of photons, like 10 to the minus 5 or 10 to the minus 10 or 10 to the minus 20 photons. Those photons go into the eye and they get absorbed by certain little molecules called rhodopsin. Okay, so the photon gets absorbed by a rhodopsin molecule. There's a large number of rhodopsin molecules in your eye. And so each time that the molecule absorbs a photon, the electron in the rhodopsin goes from one level to another, right? So the electron jumps from one level to another. So this is in the molecule, right? So the photon is absorbed, it's absorption, by the molecule. It's not by an atom, it's by a molecule. So we haven't talked about molecules in this course yet. We'll get into that when we get into chapter 8. But the rhodopsin molecule absorbs the photon. The electron in the rhodopsin molecule jumps to another level. And then essentially what happens is the molecule it essentially changes its shape when that electron is jumped. So the electrons are holding atoms together, but when the electron moves to a higher level, it can't hold those atoms together as well. So the molecule essentially twists. And that twisting then causes other molecules to change their shapes, which then sends a signal to the brain that there's been some sort of photon that's been absorbed. So your eyeball is actually acting as a photon absorber or a photon sensor. And that's how eyesight works, or at least one aspect of eyesight. Okay. So again, photons can be essentially annihilated, right? The photon went from existing to no longer existing because the energy is absorbed by the molecule or the atom. But it can also come into effect. So what can happen is you can have processes where the atoms in this light bulb are actually getting energy from electricity, and that energy creates photons, and those photons go flying out of those atoms at the speed of light, a stream of photons. Okay, so very interesting. So now here's the issue. We now have an indirect method for gaining insight into the atom itself. by using photons, what we can do is we can say, hey, you got this atom. And this atom has different levels. The electrons have different levels outside the nucleus, right? Here's your nucleus. And so what we can do is we can send in photons and do experiments, send in different types of photons with different energies, different wavelengths, and we can start studying that atom and find out what those energy levels are. So each atom has its own energy levels. So if you take a look, I see how I have different levels here for these different atoms. So this would be atom 1, atom 2, atom 3. Different elements. So one might be hydrogen, another one might be helium, another one might be, but you could also do these for molecules. So the molecule might have a totally different set of energy levels. And you can figure out what these energy levels are, again, by doing those calculations we just did. You're sending in photons with different wavelengths. You know the energy of the photon. You can look at the transitions that take place, and you can really get an understanding of these different levels that exist within the atom. I mean, what is an atom? An atom is a nucleus with protons and neutrons, and then it's also got electrons. So really all you can know about an atom is how many protons does it have? Where are those protons? How many electrons does it have? Where are those electrons? What are those electrons doing? What are those protons doing? And the way you probe that is by looking at their energies, okay? We don't have a microscope that can say, oh, let's go look at that electron, or let's go look at that proton. But we do have ways to send in photons to probe what's going on in there, right? So you're doing it indirectly. It's like you have a box and you don't know what's in the box, but you're kind of shaking the box, listening to it rattle in there to figure out how many are in there and how big they are, that kind of thing. That's essentially what we're doing with photons. We're sending in photons, measuring photons that come off to figure out what the structure of the atom is, and eventually the structure of the molecule. Okay. So any questions on photon absorption, emission, or energy levels? It's essentially one type of calculation that you have to do here. Okay, so now the next step is to talk about really the beginning of quantum mechanics. We sort of got into that a little bit. So here's some terms: quantum mechanics, or wave theory, or theory, or quantum chemistry. These are all terms that we use to describe this whole thing. So I'm going to talk a little bit about section 6.4 now, which is the deBroglie relationship. And these are called matter waves. And deBroglie came up with an amazing idea. Yep, we got 15 minutes, okay? Amazing idea. What deBroglie said was, if you think about it, light can behave like waves, but it can also be thought of as particles, right? So light is comprised of waves, electromagnetic waves. But it's also individual. It can be quantized. You have 1 or 2 or 3 of them, particles of light. We call those photons. So that means that light can behave as a wave, but it can also behave as a particle. So what deBroglie said was, maybe the electron is the same way. Maybe when you look at the structure of the atom, you got your nucleus there, and the electron is actually a wave. I'm not drawing this very well. I'll adjust it. It's a wave undergoing some sort of vibration around the nucleus. So there's just some sort of vibration occurring around the nucleus. So we would call this an electron wave. And since an electron is matter, what is matter? Matter is something that takes up space and has mass. An electron has mass. It's pretty small, but it has mass. and it takes up space, so that means it's matter, right? So deBroglie came up with this idea, and people at first sort of said this is a ridiculous idea. Why would an electron, which has mass, act like a wave? But it turns out it really does. It turns out that not very long after he did that, people started doing experiments with electrons, and they found that they could get them to behave just like waves. They could actually even do microscopes. Now there are microscopes that use electrons instead of photons, okay? So it actually does behave like a wave. So that means the electron has this duality. We call it wave-particle duality. Well, so do photons. And what that means is under certain circumstances, they behave like waves. And under other circumstances, they behave like particles. There's a duality to them, okay? So deBroglie came up with a very simple, used Einstein's equations to come up with a very simple equation to calculate the wavelength of a matter wave, including an electron. And that was h, Planck's constant, over p, where p is the symbol for something called momentum. We haven't talked about momentum, but momentum p is the mass of a particle or an object times the speed. Technically, it's velocity, but I'll use the word speed. So I'm going to rewrite this equation as h over mu. Okay, so the momentum can be calculated by using that. Okay, I'm sorry, the wavelength can be calculated by using h over mu. Now, here's what's significant about this. What you're saying essentially is that an electron has a wavelength, just like a photon has a wavelength. And in fact, even a proton and even a hydrogen atom has a wavelength. Everything has a wavelength. Even a human body has a wavelength. If I wanted to know what my wavelength as a wave is, what I would do is I would just put in my mass, put in how fast I'm moving, and put in this Planck's constant, and that would give me my wavelength in theory. But the question then is, if you calculate the wavelength of something, does it really behave like a wave or does it not behave like a wave? So in fact, humans don't behave like waves. If we could behave like waves, what we could do is if you walked up against a wall, so you started walking to a wall, you could spread your body out around the wall. And we can't do that. If we hit a wall, we're stuck. A wave, if it hits a wall, it can actually bend around the wall and move over to the other side. It can travel. Waves also spread out, right? Like, so again, if you drop that pebble on the surface of water, the wave spreads out with a particular wavelength. A human, if you drop them on water, they don't spread out and suddenly be in different places at the same time. A human is an object, a particle. So this idea of duality, the issue is, when do particles behave like waves and when do they not? So Alex gets into a particular type of problem here where you use this deBroglie relation, lambda equals h over mu, to do some calculations to determine whether something behaves as a quantum particle, meaning a wave, or does it behave like a regular, what we call a classical. So quantum, in this context, what we'll mean is, does it behave like a wave with a wavelength? Or does it behave like a classical particle? So this is just behaving like a particle. So an object that just moves with some speed. Okay, so let me show you an example. We have 10 minutes left, so I have enough time to show you an example of this. The problem here is they say, imagine an alternate universe. So you're in some different universe. And what we're going to say is that the Planck constant is different. H is no longer 6.63 times 10 to the minus 34. It's 6.626 times 10 to the 11. Okay, so you got a different universe with a different value of H. And then they're going to say, hey, you got a virus. And the virus has a mass of 8.4 times 10 to the minus 17 grams. And it's 250 nanometers wide. And it's moving at a speed of 1.90 micrometers per second. And they want to know whether this thing is going to behave like a classical particle, or is it going to behave like a quantum particle, like a wave? Which of those two is it going to behave like? Okay. So what we would say is that in our universe, a virus does not behave like a wave. A virus is big enough that it's going to behave like a particle. So you can count them, you can move them around very easily. Waves are harder to move around. So in our universe, the virus would behave classical. So in our universe. And this problem, what it's claiming is that the reason that the virus behaves like a regular, like a ball, if you want to think of it that way, or a car. It has more in common with a car than it has in common with a photon. The reason for that is because of the value h. In our universe, h is 6.626 times 10 to the minus 34 joule seconds. So it's really what determines whether something is quantum or behaving like a wave or classical behaving like a particle is really that value of h. So in this problem, we're going to use an alternate universe where there's a different value of h. So there may be other universes out there. Some physicists have postulated there may be multiple universes out there with different constants. They might have different speeds of light. They might have different values of h, that kind of thing. So let's take a look. So really what you want to do is you want to use this equation. H over mu. And then what you want to do is you want to compare the wavelength to the size. That's the main thing. You compare wavelength to size. And what happens is if the wavelength is greater than or equal to the size, then it's going to behave like a quantum particle. If the wavelength is less, really much less than the size, then it's going to behave as a classical. Okay, that's really how you tell. That's your rubric or your calculation. So let's take a look. Let's calculate the wavelength first. So again, this is the alternate universe, so we're going to use this value right here. So 6.626 times 10 to the 11 joule seconds. And then we're going to divide that by the mass. Now, I'm going to make a couple notes here. So the speed, you want to have it in meters per second. So you want to make sure it's not in micrometers or nanometers. Make sure it's in meters. And then also for the mass, it needs to be in kilograms. And the reason for that is because of this joules. A joule is a kilogram meters squared per second squared. So you need to have the mass in kilograms and you need to have the length in meters. It can't be in micrometers, okay? So H over mu, the mass is right here, but it's in grams, it's not in kilograms. So I'm just gonna do the quick conversion. We're running out of time. So I'm gonna put into kilograms. This would be 8.4. You divide it by 1,000. So that'll make it negative 20 kilograms. Okay, so notice that number got changed to minus 20 because we had to divide it by 1,000. Then micro is 10 to the minus 6. So you can do this pretty easily. Just put 1.90 times 10 to the minus 6. That's what micro is, 10 to the minus 6 meters per second. Okay? And then now what'll happen is since you've got this in meters per second in kilograms, and this is already in meters and kilograms, the units will work out. So let me calculate our wavelength. Okay. 6.626 times 10 to the 11 divided by 8.4 times 10 to the minus 20 divided by 1.9 times 10 to the minus 6, and you get, yeah, that makes sense, 4.15 times 10 to the 36. Now, it may not be obvious what the units here are. If you look at it, it looks like the units look like a mess, right? You've got joules and kilograms. So what's going on here? A joule is a kilogram meters squared per second squared. So really what you have here, I'm going to put all the units down here, is you have joules times seconds, right? So there's joules seconds. And then that's divided by kilograms. And that's also divided by meters per second. So that'll help you out a little bit there. Kilograms cancel. You have 2 meters on the top, but 1 on the bottom. So you get rid of the square on the top. And then you've got a second on the top and 1 on the bottom. So that cancels. And then you got 1 on the bottom here divided by 1 on the bottom there. So they're gone too. So you're just left with meters. So now our answer is going to be in meters. Okay, so it's not obvious how those units work out, but that's what goes on. So there's our wavelength. Okay, it's 4.15 times 10 to the 36 meters. Now, what's the size? 250 nanometers. So the size is 250 nanometers. So times 10 to the minus 9, nanos minus 9. So now we come back to this little thing right here. If the wavelength is greater than or about equal to the size of the particle, then it's going to behave like a wave. It's going to behave like a quantum wave. And so it looks like, if you take a look at it, this is much bigger, right? The wavelength is much larger than the size. So that means it's going to behave like a quantum particle. Okay? Now, here's what would happen in our universe. I got 2 minutes left here, so let me put it in here. If we used our universe, we would use the different value of h, 10 to the minus 34. Okay, so here's what happens. If in our universe, the wavelength is different. It's 4.93. Oh, it should be 4.15, sorry. 4.15 times 10 to the minus 9 meters. Okay, so in our universe, the wavelength is smaller than the size by quite a bit, by about a factor of 50 or so. So in our universe, the wavelength is smaller than the size by quite a bit. It's a lot smaller in size. So it's going to behave like a classical particle. So if viruses behave like waves, you would actually have some interesting things you could do with viruses, but there would also be some dangers. They would be able to actually do something called tunneling. They would be able to move through a cell membrane, for example, just by having some probability they could move through. So in our universe, they can't do that because of the value of h. So there you go. So for that one, again, just be careful. Make sure that you have the mass in kilograms and the speed in meters per second, and then you can just do this calculation according to this right there. Okay. So that is deBroglie's relationship, and deBroglie's relationship is in section 6.4. Okay, so what we've done is we've looked at waves, we've looked at the matter waves now. So now what we're going to claim is that the electron behaves like a wave. And what that means is if it behaves like a wave, we have a completely different set of physics rules that it's got to obey. So in section 6.5 and 6.6 and 6.7, which we'll start on tomorrow, what we're going to look at is we're going to look at the electron as a wave. deBroglie's calculation shows us that the electron in an atom can behave like a wave, so we got to apply the rules of waves to dealing with the electron. Okay, very good. So let me, I will save this and post it on YouTube today. And the lab reports that were due yesterday, I haven't graded those yet. I'll start working on those today. And I hope you have a great day. Reach out to me if you have any questions or need any help. And good luck in everything you're doing this week.
Thank you.
Absolutely.
Thank you.
Have a nice day.
You too. Bye-bye.